Well, T inverse AT turns out to be really easy to calculate once you have your T inverse and your T. And where's my red chalk? Good heavens. It's conspiracy. Okay, so T inverse AT. Well, here's your T inverse that we calculated a minute ago. Here's your T matrix, column of eigenvectors. And here's your A matrix. And if we do this calculation, which is very straightforward, well, I multiplied this matrix by this because that was easy. And then I multiplied this matrix by this. And I got this. What do we have? This is a diagonal matrix. All your non-zero entries in the diagonal, zero everywhere. Non-zeros on the main diagonal, zeros everywhere off of the main diagonal. And lo and behold, the numbers you get here are your eigenvalues. Well, this is a diagonal matrix. And getting the ability to transform a matrix to an diagonal matrix with the eigenvalues on the diagonal is really a great big deal. As I hope you know from your linear algebra, but again, diagonalization, we don't always end up with enough time to do that in the detail it deserves, at least in a very introductory linear algebra class. In any case, what I say here is A been done diagonalized. A has been diagonalized, to put it in less formal language. Okay. We also say that the T inverse AT, the diagonal matrix, is similar to A, meaning that it has the same characteristic equation. Now, we worked out the characteristic equation for A. You can work out the characteristic equation for this. And if you just write it down, it's very easy to see that it's the same as the characteristic equation we had previously. We're not going to go into the theory of why that happens. That's your linear algebra, but we're going to use that fact. Okay. Now, I will note that a rotation of R2, for example, has no eigenvectors. So not every matrix A that we could write down, not every matrix A that comes out of a system of linear, of differential equations is going to have eigenvectors. Okay? Eigenvalues or eigenvectors. Why is that? Because, well, if you're rotating a vector, if you're rotating all the vectors in R2, then there is no vector, like the V1 we had before, that maps onto a multiple of itself. Because it's been rotated. It's not in the same direction as it previously was. So, rotation of R2, there's no eigenvectors. If it's rotated, its direction changes, and by it, I mean if a vector is rotated, that's what I mean by its. It is. If it is rotated, and IT apostrophe S means it is, ITS doesn't mean it is. If I write IT apostrophe S here, I'm saying if it is rotated, it is direction changes. That's not right. Okay, well, a little grammar lesson. If it's rotated, its direction changes, so it don't know how to map to a multiple of itself, to put it in formal mathematical language. Okay? If a vector is rotated, then it is not by transformation, then it does not map to a multiple of itself. Okay. So that's kind of important to know. Not every matrix will have eigenvectors. And when you get into higher dimensions, you might have whole subspaces that map, that have eigenvectors, but you might also have other subspaces that get rotated in some way and don't have any eigenvectors. So as a result, it's not always going to be possible to write down your T matrix, because your T matrix has to have a full set of eigenvectors. If you don't have a full set of eigenvectors for your n-dimensional space, don't have n eigenvectors, then you're not going to have n column vectors to write here and be compatible, and be, in first place, invertible, and second place, compatible with your A matrix. Okay, So try to understand what I'm saying, but let's move on with this specific example.